What's up, fellas? In this video we're going to talk about some of the specifications of this waste oil burner that I've been working on. Some guys have asked questions about the actual dimensions and some of the angles that I've got going on here. So we're going to talk about that a little bit, and we're also going to look at fuel consumption, and we're going to be throttling the air-fuel ratio this time around. The last few times I ran this, I did not have this valve on here, and what that's going to allow us to do is modulate the oil intake, which should give us some pretty hot oxygen-rich flames. My plan is to reduce the oil flow, which I'm thinking ought to produce a shorter, hotter flame. And in addition to that, a couple of guys who are interested in using this design for a foundry have asked me if this thing can smelt copper. So what I've got going on here is a small crucible, and we're going to try and see what happens to these specimens in the flame, just to get an idea of how hot it is. Got some aluminum and copper and some steel. Okay, before we get to the testing, let's talk about some of the features that were listed here by discovery. This isn't just something I decided I want to do. Several people have asked me, why don't I just use a straight pipe? Well, the reality of the matter is I do have footage on that very concept not working at all. For whatever reason, guys, this elbow is absolutely essential to the working of this device. One of the two important features that you're going to want to remember is the position of this needle is somewhat calibrated. I had to discover that through testing, sliding it back and forth and also bending the angle. And it turns out that a 41-degree angle, 17 millimeters in from the throat, is an optimal position for that air siphon. I also wanted to point out the benefits of a siphon nozzle. First of all, because we are blowing air into this chamber is causing something called, like it's almost like a Ventura effect, but it's not. They have these devices called ejectors that work under the same principle. A high-speed jet of either fluid or a gas is blasted into a small chamber, and it causes the air pressure in the surrounding area to drop, resulting in a vacuum. In fact, some of the most powerful vacuum systems that can be built use the ejector principle. They'll use high-pressure steam and blow it into a tube like this, and it causes a vacuum. So in effect, the air compressor is actually pumping air through this hole in the top of the unit. So the device itself acts like an air pump because the air pressure is spraying air molecules at high speed down into the combustion chamber, and they collide with ambient air molecules and accelerate them in that direction. And in addition to that, as I said, there's also a vacuum caused by the sweeping away. But anyway, in addition to that, I discovered that this steel plate is a necessity for long-term use because, as you can see, my nozzle is pretty fouled up there. The flames come flying up out of the back end of this thing in like almost a pulse jet kind of behavior. And this mitigates that issue, and it also brings it down to about 100 decibels because the thing is really loud as it is. By having this plate on here, it's a more steady, constant flame, and it doesn't have that high frequency pulse jet sound to it. And I think it even seems to burn a little better this way, personally, just from observing the flame through the camera. When you move this plate off, the flame will get dimmer. It almost washes the camera out when you have this plate on versus when it's off. You can define the entire flame versus with it on. So that's one of the cool things. And I just wanted to point out the fact that the air compressor, although it is spraying combustion air into this chamber, that's what makes this particular chamber essential to the operation of this device. Sure, we could build an oil nozzle that sprays oil atomized so well that it produces a naked flame, and we could use that, but the problem is it's a lazy flame. It has no jet to it. It can't be forced into a forge or something like that. It's just too lazy of a flame. So what this device allows us to do is it's using the air jet as a means to induce a Ventura effect, so to say, and in principle turns this device into an ejector. I have some pictures of ejectors. Okay, fellas, so this is a highly efficient ejector. Of course, we don't have a divergent, convergent nozzle, which is how you would optimize that. They use them in a water. Also, your toilet, by the way, you know that pump in your toilet, that little water nozzle? That's basically an ejector. That's a very good example of what an ejector pump is. The way your toilet pumps water out of that bowl is this process right here. It uses an ejector. I'm not exactly sure what they're calling that. I think it's a Ventura, isn't it? Even though it's not configured in the standard, you know, classical description we see in a book with a tube at a right angle to an air source. This is a better illustration of the ejector we have. There's no divergent nozzle, but these things produce one hell of a vacuum. In fact, I'm surprised they're not showing us any vacuum. These right here are the ones that produce massive vacuum right here. So in effect, not only does this chamber double as a vaporization means, because it gets so hot, any oil vapor or oil splatter that touches this canister is going to be instantly vaporized into a combustible gas. But in addition to that feature, it also acts as an ejector pump, which enables this high velocity, low volume flow of air to force a larger volume of medium velocity air out of the combustion chamber. So we're getting a 2-for-1. This thing is actually doubling as an air pump. Even though it's ejecting 4.5 cubic foot per minute, we're probably tripling that with the ejector concept. The oil is also adding to that ejector principle. Now, when I tried to run this in a straight pipe, I believe the ejector velocities were just too high for the flame to stay inside of the combustor. I don't know what the real kinematics behind it are, but it just wouldn't work. Having this 90 on here is the only way I could get this thing to work this small. Now, why is it important that this thing is so small? Well, if you've seen a lot of the waste oil burners online, they're huge tank-like devices that have a massive fireball inside of them that is requiring on the order of 100,000 watts of energy to do what it's doing. So if you're using this for heat, that's fine to have that massive fireball inside the combustor. But if you're using this as some kind of workhorse, say for a forge or to burn paint off something like I did with that tank over there, you want your fireball where the work's being done. You don't want a big 100,000 watt fireball inside of a tank that's doing nothing for you, especially not if you're doing this for a forge, because it's going to take a lot of oil. One of the things about this particular burner is that the amount of oil I use for the amount of usable flame I get, it's like 10 times better than anything I've ever run. I use these things to burn tree stumps out of the ground, so I need my fireball right there where the work's being done. Otherwise, I'm just wasting oil. This stuff isn't free, and it doesn't last very long. You'll burn 4 or 5 gallons up in no time with those big, beastly tank-type waste oil burners. They just aren't very efficient. They're kind of a waste of your oil. So if you're looking for a design that can save you oil, this thing is far better than anything I've ever run, and I've built quite a few of them. Now, as far as the airflow that I've been using to run this device, we're looking at 4.5 cubic foot per minute at 90 psi's. I run this thing right around 100 psi's, so I'm not sure the actual cubic foot per minute. The compressor does not run continuously, so it leaves one to wonder if a really nice airbrush air compressor could run this thing. But then you're spending a lot of money. In my case, my air source is free. I already have this air compressor. So if you're using this for a forge, chances are you already have an air supply. So this particular design right here, the only thing I had to spend money on was this needle valve. I already had the needle valve, and with some serious modifications, I turned this into a siphon pump. or a siphon nozzle, as some people are calling it. I have another video that gets in to the details of building one of these. I'm not going to focus on that here, but because some guys have asked for some plans, I don't really have any plans. All I have is my little log book. Whenever I build something that works halfway decent, I tend to put it in this book I have here. That was a fun one there. Biuld lawnmower. If you haven't seen this video, you got to check it out. This thing was so cool. It's definitely never going to be a consumer product because I don't think I could get a UL rating on something that shoots a 9-foot flame out the side of it. Definitely cooler than hell though. And it is better than raking. It burns leaves basically. That right there's a combustion chamber with a leaf blower hooked up to my lawnmower. Yeah, I do some pretty crazy stuff. But at any rate, there you have it. Today we're going to put some data on our acquisition book here because I'd like to be able to consult this stuff later on. This particular burner, last time I rated it, was hovering around 45,000 watts. That's based on calculations you can do using the oil consumption, because we know how many megajoules of energy we get per liter. You use how many liters per hour and yada yada. I have a video on that also. I'm not going to bore you with that. So, had an individual ask me if this device can smelt copper, and I told him I believe it could. So today we're going to put this flame to work on this array of specimens, and we're going to see if we can get us a puddle of copper inside of that thing. Now, it is like colder than hell outside right now, and this is going to affect my oil. I tried to heat this oil up a little bit. Your oil temperature is going to be pretty important. This is synthetic oil, so it's not all that big a deal. And I also added this much gasoline to it. That was another topic of this video, is I do something I guess you would call fuel blending. I often don't use straight oil during ignition because it's just not worth your hassle trying to spray straight oil into a cold waste oil burner. It's better just to make a hot mix for ignition and then go to straight oil after that. In addition to that, I found myself pondering what would happen if I did in fact blend a 50-50 mix of oil and gasoline. Would that do something more than just make a amazing video? I'm more about practicality here. It's not all about show, so we might do that. I don't know. For now, that's how much gas we got. This oil is 77 degrees, and we're going to fire this thing up. I'm going to see how long it takes to burn through 1 liter of oil at 100 psi's, and then I'm going to bring it down to 50 psi's and see how long it takes to burn out that last liter of oil. And I believe, I think it was 2 point something. Okay, 5.5 cubic foot per minute at 40 psi's is available. We won't be using that much. And now that I think about it, because this compressor kicks off for a substantial amount of time, the actual cubic foot per minute that I'm going to be giving you guys is not going to be accurate. I am simply using these figures to describe to you the amount of air compressor power that you will need to make this thing run as observed. Now, you can probably use a little bit less than this because this thing's kicking off for me for quite a while. It seems like it doesn't run much at all. So this thing's going to be really loud, but as I said, these aren't exact figures, but at least you'll know you'll need a compressor that can provide 4.5 cubic foot per minute at 100 psi in order to be even close to running this thing at a usable rate. I don't know what I was trying to say there. A candidate. That's what I was trying to say. Before it's even a candidate. So we're going to do test 1 at 100 psi's, and we're going to see how long it takes to burn through the liter of oil. and we're going to get a liters per hour figure off of that information. The reason why I need the liters per hour is because that is a figure used in the calculation that determines the actual kilowatt output of the waste oil burner. And the reason why I'm providing that information is because some of these people who are building forges, that's kind of good information to know. You kind of want to, if you know you've used a forge that's only 50,000 watts, and you know how that forge worked, and I'm showing you something that's 70,000 watts, you know it'll work for what you're doing. You might know that you need a 100,000 watt forge, so you would need twice the air, twice the oil. So that's the reason why I'm giving the wattage. Plus, it's just really cool to see how much power these things actually put out, and it's freaking amazing that you're getting like almost 50,000 watts of power out of this thing. I can't remember how many horsepower that is, but 1 horsepower is 745 watts. Okay, fellas, so in test 1, we're going to be conducting 2 tests simultaneously. The first one being the actual fuel consumption of the device, and the second one is to answer the question of the gentleman who wanted to know whether or not this thing could power a forge to smelt copper. So let's see what happens here. Okay, fellas, so here's the scoop. I was not running at this thing's maximum operating level. It can run a little bit higher than 100 psi's. I was just doing that for the purpose of cataloging its performance. It almost melted the copper. That took us about a little over 14 minutes. So we're looking at 4.2 liters per hour, which is right at 1.1 gallons an hour of oil. I removed the hose halfway through the test that has the oil throttle valve on it because I can tell by the size of the flame this thing isn't running as good as it could have been. I added an extra length of hose to it, and that kind of inhibited performance. So just adding that extra piece of 4-foot hose right there with that valve, in my eyes, significantly reduced the performance I witnessed last time at the same setting. So the size of your oil hose, you want that to be a pretty good size. I did go for a size bigger than this 1/8 inch nominal, but it still seems to be restricting a little bit, and I'm under the impression that maybe I ought to place my oil reservoir in an elevated position. Even though it has a siphon on it, it will still benefit from the gravity effect of the induced siphon of an elevated reservoir. So that would give me a higher oil flow. Also, I'm thinking maybe the nozzle that I have could be made a little bit bigger. I would consider this a low setting nozzle, so I'm probably going to build a different siphon nozzle that has a higher oil flow rate, because not getting the oil flow rates I really want to see. This is what we ended up with. Let me grab some gloves. The copper just started to melt. I don't know if you can see that blob right there. It was on the verge. It didn't quite. That actually may have been from the last test I did when I stuck this inside the combustor. But yeah, we just got us a bunch of flake. Now, I only ran this for 15 minutes, and I've never operated a forge before. I would imagine a forge probably takes a good hour before it gets up to melting temperatures, as far as if you were to throw a bunch of stuff in a forge. I could see it taking an hour to finally get to smelting temperatures. We did melt some aluminum at the last couple of minutes. This was just a last-ditch effort to see if this flame could do anything, because it was apparently doing nothing. But as I said, this thing wasn't operating at high of a level as it was last time. So there's a potential that it could do better. So what I'm going to do now is go ahead and stop the test, because it's getting late in the day. People are getting off work, and this thing is so loud, my ears are screaming. So I'm not going to do any more testing today. The next test, I think I'm going to skip the 50 psi, because we don't want to see anything less than what we just saw, and I really don't think I need that information. Doesn't appear it's going to be able to do much at that rate other than burn tree stumps out of the ground, and I'm sure simple arithmetic could get us where we needed to be if we had to think about that. So the next test we're going to do is going to be at full throttle. I'm going to bring the pressure up as high as that compressor can run it, and we'll see what it does there. I believe it only runs at like 105, 110 psi's, but the flame is bigger. And I'm going to try to melt copper one more time, just out in a naked crucible. I don't know how effective I should expect that to be, but it did not melt any of the specimens. It did get them to start changing colors and doing that iridescence that copper does when it gets hot. So I brought it to the temperature of iridescence. If anybody knows what that temperature is, please leave a comment. I don't have time to look that up right now, but it is interesting. So there you have it, guys. The thing just wasn't pumping the oil I wanted to see. I tried to throttle the valve to see if we could get a higher oxygen flame, and I kept killing it every time. And I was worried about the explosion hazard that could have potentially been caused by the vaporization of those large clouds of oil and then reignition. So that got kind of scary there for a minute, and I need more time. And sometimes on experiments like this, I kind of need a second set of hands. I've got too much going on at once. I'm paying attention to watches and data on the cameras and pressure and all this other stuff. So I have to sometimes go back through the footage, but at any rate, for you guys who were asking me if this thing could smelt copper, I can't answer that yet, and I apologize, but I tried. I gave it hell today. My girlfriend's probably pissed. This thing was loud, man. From working in power plants, I got a pretty good idea how loud stuff is, and I want to say it was well over 100 decibels in this garage. Do not run this thing without ear protection. It is definitely in the hearing damage range. You ought to hear it with this metal plate taken off of here. You get about another 5 decibels out of it with that plate off. Plus it fouls up my siphon nozzle in. So that's the main reason I decided to leave it on there. The second reason was, as I said, the flame appears hotter with that on there. It's a better fuel to air ratio, I would imagine, is what's going on. And it seems to streamline the flow. But I've got a little bit of a mess here. I'm going to do some math, and we're going to figure out what wattage we were running at 4.2 liters an hour, and we'll go from there, fellas. As I said, I've never ran a forge before. Any of you guys who are building these forges or who have ever run a forge, could you please leave me a comment and let me know the typical time required to bring a forge up to temperature, and then how long it would take to melt, say, let's say 5 pounds or so of copper. Any of you guys who've ever done this. I'm really curious, actually, from you guys who have actually done it before. Because as I said, I can't answer your question. We didn't see any melt within 15 minutes. But this was naked. This is right out in the air. And one of the things about doing it naked is you lose a lot of infrared radiation. When you're running inside a crucible, the fire brick lining begins to emit thermal infrared radiation that kind of contributes to the heating of the crucible. So you don't get that. In fact, you get the opposite. You get the loss of infrared radiation, whereas inside the crucible, the infrared radiation being emitted by the substance that you're heating is trapped. Outside, those rays are just giving me cataracts. So I'll get that data for you guys. We'll go ahead and wrap this test up for the day. Wasn't getting the oil flow I wanted. As you see me, as you saw, I pulled the 4 feet off during the test. I also didn't get my time right, guys. That 14 minute, 22 seconds is, there was some fiddle around in there. Like I said, I had so much going on at once. So this was a total failure, this test, in the sense that I didn't get completely accurate time. I could be a few minutes off, I don't know. The way things went down, it was bad from the beginning. That happens in experiments sometimes. You get it all planned out, and then next thing you know, all hell breaks loose. For instance, this thing went out on me twice and nearly produced an explosive environment. In addition to that, just wasn't working right. So my oil consumption is going to be off. Looks like I'm siphoning oil, damn it. Oh, I am. I just got to looking down at that. Ah, the joys. So this is what I get to do. Got my filter hanging up there. I can't stress enough the importance of filtering the oil with this kind of nozzle. This is a little rig that I built to do just that. There's basically some screens in there. I have a trap door that I can open to get the stuff out, or I can just open it at the ends. But there's no screens on the one side. Yeah, this side here has no screens, and I have screens on this side here. And that's what I use to filter the oil. You have to filter waste oil. I don't care how clean you think it is. There is stuff in motor oil that I just don't get sometimes. Bugs, all kinds of stuff. It's weird. So there you have it, guys. Total failure, but it was kind of cool to look at. So as I suspected, I may have a clog or something in my nozzle, or it was just so cold out today that the oil wasn't flowing right, because I should have been around 43 to 46 kilowatts. We were only running at 4.2 liters per hour, and it's typically 4.4 to 4.5 based on the video footage I reviewed. So something was up with my oil flow, probably that long piece of hose that I had on there. adding that 4 feet really affected me. So I'm gonna have to do something about my oil flow and may actually build a bigger siphon nozzle. So we're at 41.8 kilowatts. Where is my calculator? Just use this one. If that is, okay, 41.8 times 1,000 to give us our watts divided by 745. We're looking at a 56 horsepower burner there, which is just not enough. We were unable to melt all the specimens, so we're going to give that another shot. I'm going to probably end up building a bigger siphon nozzle or going with a gravity feed on the siphon nozzle. I'm going to hook up this old gravity feed setup. It came off an older oil burner that we used this very filthy oil tank I'm going to have to clean. The tank would just sit on there like that and you just dump oil in it periodically. It burns it slow enough that this is a fairly good size. I think you get about 15 minutes out of this can. You really don't want to leave this thing unattended anyway, so it doesn't hurt to keep adding oil to it. This is not a heater, so for me that works out okay. I'm usually burning out tree stumps as this thing's main job for me. It's very good at that, especially if you have a tree stump that's grown into a fence and is impregnated with fence. That can be quite a problem. It'll tear up your chainsaw real quick. So there it is, we're done. I'm gonna have to do something to this thing. It's just not working the way that I know it can. We're gonna have to build a different nozzle. So I'm gonna go ahead and work on building a better siphon nozzle, and then we're gonna see what this thing can do. We want to see about 60 kilowatts at least, or 80. I'd like to see 80. 100 would be huge. It'd be like a 5-foot flame. So next time we see this burner in action, I'm hoping to see this number here at least up to 80. I need a much hotter flame than that. Our oil valve failed. It was 14 minutes and 22 seconds. Oil temperature going into the device was only 77 Fahrenheit, which is still pretty thin. That is the approximate air consumption. That's just guesstimated. I don't know for sure. I also need to run this device at the highest pressure that air compressor can crank out. So we're going to be seeing what pressure that is. I believe it's around 105 to 110 PSIs, which would also kind of explain why I didn't see those higher values this time. I wasn't thinking about that. Pretty sure I had it running full tilt last time. So there's a lot to it. We're going to get us a little bit of a data set here, and as I said, I'm going to build a different siphon filter or siphon nozzle.